For this video, we will compute the fictitious forces, also known as inertial forces, that arise in a rotating frame of reference. We go on to use this knowledge to compute the motion of a Foucault pendulum. We describe the Eötvös effect, the deviation we expect from a sniper shot, and how these forces affect weather systems. Before we discuss rotating frames of reference, we will introduce some notions from the theory of Cartesian tensors. First off, we define delta ij. This quantity is called the Kronecker delta, and it's equal to 1 if I equals j, and 0 if I does not equal j. I and j here are indices running from 1 to 3. So they're the x, y and z components. Epsilon ijk is called the alternating tensor, and it takes the value 1 for an even permutation of 1, 2, 3. In other words, ijk is an even permutation of 1, 2, 3. So ijk is either equal to 1, 2, 3, 2, 1, 3, or 3, 2. That should be 2, 3, 1, or 3, 1, 2, minus 1 for an odd permutation. So ijk equals 2, 1, 3, 3, 2, 1, or 1, 3, 2, and 0 otherwise. So this happens in the case that any two of the indices are the same. Now, epsilon ijk is an example of what is known as a totally antisymmetric tensor. So if we have aijk being totally antisymmetric, which means whenever I exchange any pair of indices, I change the sign of a. So for instance, that's minus a, k, j, I, for instance. And the same sort of relationship holds with any swapping of any pair of indices. Then aijk depends only on one value, a123 times epsilon ijk. So for instance, if ij and k are 1, 2 and 3, I get what I want. If I swap any pair of indices, I end up with a minus sign from here times this original value. Let's consider Cijklmn as determinant of delta il, delta im, delta in, delta jl, delta jm, delta jn, delta kl, delta km, delta kn. Now, using what we know about determinants, I know that if I swap any two rows, I change the sign. So if I swap I and j over, I swap this row with this row. And that has the effect of changing the determinant by a minus sign. And I can do that with any of the rows. So swapping I, j or k with one of the others introduces a minus sign. Therefore, this is totally antisymmetric in I, j and k. So I can write this as C123LMN epsilon ijk. That's using this earlier result. But now I can play the same game with the columns. If I swap L and M, for instance, that effectively changes these two columns. And swapping two columns changes the determinant by a minus sign. So this is totally antisymmetric in L, M and N. So this is also equal to C123 1, 2, 3, epsilon ijk, epsilon L, M, N. But what's this thing? If we put 1, 2, 3 for I, j and k, and similarly 1, 2, 3 for L, M and N, we just get the determinant of the unit matrix, which is 1. So that's epsilon I j k epsilon L m n. And I can expand this thing out. It's delta I L delta j m delta k n minus delta j n delta k m minus delta I m delta j L delta k n minus delta j n delta k L plus delta I n into delta j L delta k m minus delta j m delta k L. Now the result we will really be using is when two of these indices are the same, so epsilon I j k epsilon L m k. Now when you have a repeated index, there is implicit summation over the values 1, 2 and 3. This is known as the Einstein summation convention. And the effect, for instance, of having delta I j E j dot 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 is equal to B I dot dot dot. The delta acts as a substitution operator because this is only non-zero when I equals j. So for instance, when I equals 1, in this sum here, j is summed over, the only term which gives something non-zero is when j is equal to I, which in this case is equal to 1, so I only get B1 whatever, and so that's just corresponding to substituting the value I for j. So here, we're setting n equal to k. Okay, delta kk minus delta jk delta km minus delta im delta j. Here's a curve. Delta kk minus delta jk delta kl plus delta ik delta jl delta km minus delta jn delta kl. Now delta kk is 3 because it's actually delta 1 1 plus delta 2 2 plus delta 3 3, and each one of these is 1. So we get 3 delta IL delta JM minus delta IL delta JM, that's using the substitution rule here, minus delta IM times delta JL, and that's a 3, plus delta IM, and this acts as a substitution operator, JL, plus delta IM delta JL minus delta IL delta JN. So ILJM there, and there, so I get delta IL delta JM minus delta IM delta JL. So that's what we get for this thing. Another property of the epsilon ijk, that's epsilon kji with a minus sign, which is epsilon jki. So you can see I've just cyclically moved this from the beginning to the end, and so that will be useful later on. Now let's discuss rotations. Let's draw the disk there. Here's the origin, and this is the unit normal, so n squared is equal to 1. that vector be x, then this vector here is x dot n, that's the length, multiplied by n, and therefore this thing is x minus x dot n. Now let's rotate about n, so we're going to rotate by angle theta. Well, let's drop a perpendicular there. So this vector is orthogonal to this vector here and to n. So we can construct it using the cross product. If I move from vector x to the vector n, then you can see that we move in this way here. So x cross n is coming out, so that's in the direction minus n cross plus n cross x. What about the magnitude? Well, n cross x is n cross x minus x dot n. And this vector is orthogonal to this thing, so the norm of x cross n is the norm of that times the norm of this thing times the sine angle between them in magnitude, which is 1. So n was a unit vector. So this is of the same size as this, and therefore we can write this vector here, x prime, is x dot n n plus cos theta x minus x dot n n. That's that part there. And then we have sine theta times n cross x, and we call that rotation with axis n and through an angle theta. The next thing we're going to do is consider an antisymmetric matrix, or in this case, strictly speaking, a tensor. It satisfies aij is minus aji. So this just has two indices. Let me define alpha k to be equal to a half epsilon I j k a I j. And let's see what happens if I multiply this by epsilon I j k. So we go half, we have epsilon I j k. Now I and j are summed over, so I can also write that as epsilon L m k a l m. It doesn't matter what I call the thing I'm summing over. So epsilon L m k a l m. But this thing is something I worked out not too long ago. It's delta IL delta JM, delta IM delta JL ALM. And from our result about substitution, the first one replaces the L by I and the M by J, and the other thing is round the other way. But this is antisymmetric, so that's just AIJ. Okay, so we're going to be using this result in a moment. Going back to the rotation, let's work out partial derivative with respect to theta. First principles, that's the limit h goes to 0 of the rotation n of theta plus h minus rotation n of theta divided by h. Property of rotations about a common axis is that that's going to be given by the limit h goes to 0 of the rotation n h minus 1 over h times r n theta, because rotation by combined angle alpha plus beta is just you do a rotation by angle beta and then you do a rotation by angle alpha, and that's equivalent to rotating by angle alpha plus beta. So that tells me that's the partial derivative dn theta by d theta at theta equals 0 times r n theta. Okay, so what is d by d theta r n theta times some vector x? So theta x. Let's just call that thing y for the moment, and that's about at theta equals 0. So recall r n theta times y is equal to y dot n plus y minus y dot n cos theta plus sine theta times n cross y. So if I differentiate this and set theta equal to 0, this gives nothing, this gives a sign which vanishes, this gives 1, and so we get dr r in theta by d theta at theta equals 0 is n cross y if we apply that to y. Therefore, r of n theta dot times y is r dot n theta r n theta inverse of x equals n theta dot crossed with r n theta inverse x. Let's say at times 0. So that's 0. So we're going to define x of t to be r n theta x of 0. That's equal to omega cross x of t, where omega is n theta dot. So what we see is that omega, which is the angular velocity, is the product of the rate at which we are moving around an axis and the direction of the axis. If the axis itself is going to vary in time, then we get this result, but with n replaced by the instantaneous axis of rotation at any point, and theta will be the instantaneous rotation rate around that axis. Next, for any rotation, the inverse is the same as the transpose. So r times r transpose is the identity. Let's take the time derivative of this. We get that. And if A is r dot r transpose, then A transpose is r transpose transpose r dot transpose. That's r dot transpose. This is a plus A transpose is 0. It says that A is antisymmetric. So I can write omega subscript k is minus a half epsilon I j k a I j, and a I j is minus epsilon I j k omega k. So omega is minus alpha in the previous working. Now I know that A is r dot r transpose, so we start off with x of t is r of n of theta x at 0. Let's differentiate this, and we're going to assume that x is a point which is not moving in the frame, but it moves with the frame. So that's r dot n theta x of 0, and that's equal to r dot n theta r n theta inverse x of t. So that's equal to a times x of t. But a was antisymmetric, so x subscript I of t dotted is going to be a I j x j t. That's minus epsilon I j k omega k x j as a function of t, and that's minus x cross omega ith components in terms of the cross product. So that's omega cross x ith component, or x dot is omega cross x. Now let's consider a basis which is rotating with the frames. We'll have that EI for I equals 1, 2 and 3 being a basis. Then we have EI dot is omega cross EI. And now let x be xi EI. Again, we have summation implied here. And here we'll also assume that xi and EI are both dependent on time. So x dot is equal to xi dot EI plus xi times the derivative of this, which is omega cross EI. So that's xi dot EI plus omega cross x. Well, this is the derivative, time derivative of x in the inertial frame. This thing is the derivative of x if you measure everything in the rotating frame, and that's omega cross x. So this applies for any vector x, not just position, it could be velocity, for instance, or acceleration, or any number of other things. Next, what we're going to do is apply Newton's second law in the inertial frame and see how that translates into the rotating frame. So d2x by dt squared in the inertial frame, we're going to write that as the force divided by the mass. That's d by dt in the rotating frame plus omega cross dx by dt in the rotating frame plus omega cross x, and that's equal to the force over the mass, or d2x by dt squared in the rotating frame plus 2 omega cross dx by dt in the rotating frame plus omega cross x, and finally there's an extra term which isn't often written down, omega cross x, omega dot cross x equals that. Let's rearrange this. d2x by dt squared in the rotating frame is minus 2 omega cross dx by dt in the rotating frame minus omega cross x minus omega dot cross x plus f over m. We call this the Coriolis acceleration. We call this thing here the centrifugal acceleration. And this is the Euler acceleration. Just call it the Euler term. And these are the other forces. So if we're measuring our velocities or accelerations or positions in the rotating frame, then we have Newton's second law again, but we have these three extra terms. Let's apply our understanding that we've gained so far to the case of the Foucault pendulum. So in this case, omega is going to be the angular velocity of the Earth. So let's draw the Earth there. Omega points directly up through the North Pole in this case. Let lambda be the latitude, and I'm going to call this vector Ez. That's a unit vector which is radially upwards from the point we wish to consider on the Earth. We're going to introduce basis E east, E north, Ez, and then this basis will be right-handed orthonormal. So let's just draw E north in here, and we can see omega is scalar omega times naught for the components in the easterly direction. In the northerly direction, well, that will be lambda there, so we're going to get cos lambda sine lambda, and omega is 2 pi radians per day. So for the Foucault pendulum, we consider a mass m, say, of a pendulum of length L. If we were to disregard the Coriolis term, then we would have the equations x double dot is minus omega squared x, y double dot is minus omega squared y, where vector x is x, y, z, and omega squared is g over. So let's now consider what happens in a rotating frame. If we neglect this term here, the centrifugal term, it's quadratic in omega, and just concentrate on the Coriolis force, the Euler term already vanishes. Then we get x double dot, y double dot, z double dot. Dot now means in the rotating frame is minus 2 scalar omega, or cos lambda sine lambda cross x dot y dot z dot minus omega squared x y z, which is minus 2 omega. The first component is given by that times that minus that times that. We assume that z dot is 0, so the motion takes place in a plane. So we're going to get at least a good approximation. So we get that times that minus that times that. That's minus cos lambda y dot. This component gives me sine lambda x dot. Let me just check that. No, that's a sine. And I don't really care about that term there. Minus omega squared x y. I don't really care about that term. So x double dot is 2 omega sine lambda y dot minus omega squared x. Y double dot is minus 2 omega sine lambda x dot minus omega squared y. I want to solve these equations. The little trick is to use the complex variable, zeta being x plus iy. Then we get zeta double dot equals minus 2 I omega sine lambda zeta dot minus omega squared zeta, or just rearranging. Okay, that's a second order linear differential equation with constant coefficients. So we can write down a solution. Zeta, you complete the square, so let's do that. R e to the minus I omega sine lambda times t cos omega primed t minus t naught. Omega primed is the square root of omega squared plus little omega squared sine squared lambda. Take the real part, r cos omega sine lambda t times cos omega prime t minus t naught, and y is r sine minus sine. So therefore y is minus tan omega sine lambda t times x. So there's x, there's y. If that is omega sine lambda t, then because the minus sign, we're moving clockwise. The plane of rotation of the Foucault pendulum is moving at a constant rate of plane of rotation. It self-rotates at a rate of omega sine lambda in the clockwise direction. At least in the northern hemisphere, it will be in the clockwise direction. In the southern hemisphere, it will be the anti-clockwise direction. You take the modulus of this thing. Next, we're going to discuss the Eötvös effect. So x double dot is minus 2 omega cross x minus gez, where g is the acceleration due to gravity. Dot on there. We'll consider x dot being VE, Vn, 0. So we're looking at the motion of a body which is essentially horizontal, where the horizontal component of the velocity is a lot larger than the vertical component. That's minus 2 scalar omega times 0 cos lambda sine lambda crossed with VE, Vn 0 minus 0, 0, g. And that's equal to minus 2 omega minus Vn sine lambda Ve sine lambda, and the last component is Ve cos lambda with a minus sign. In particular, the z component, z double dot, is equal to 2 omega Ve cos lambda minus g. Let's call that minus g primed. This is the effective gravitational force that we would experience. So if, for instance, you are flying in a plane in a direction which is easterly, so Ve is greater than 0, then you would see a reduction in the effective value of gravity. And for instance, if you would take a weight and put it on a suitable spring balance, it would weigh less if you were travelling in the easterly direction than if you were not moving at all. And correspondingly, if V is negative, in other words you're moving west, then it will weigh slightly more. Next, let's consider a marksman aiming at a target and what effect the Coriolis force has for him hitting the target. So we have x double dot, y double dot. We're not worried about the z direction at the moment. We essentially have the same setup as we have here. So that gives me 2 omega Vn sine lambda minus 2 omega Ve sine lambda, 2 omega sine lambda Vn minus Ve. So if this is our direction V, Ve, Vn, that's the northerly direction, that's the easterly direction, then this lies in this direction here, which means there's an acceleration which is going to move the bullet off to the right if we're in the northern hemisphere. How much is that deviation? Well, in here I've essentially assumed that the velocity doesn't change by very much during the course of its trajectory. So the displacement will be a half a t squared, where a is that thing there. We're going to assume that the target is a distance d away, which is mod v times t. So we get omega sine lambda times mod v t squared times er, where er is the unit vector in this direction. So that's omega dt sine lambda ER. This is the displacement of the bullet to the right in the northern hemisphere. And it's important to notice that it does not depend on the direction in which you fire the bullet. You get the same deflection in all cases. Additionally, we get a deflection in the vertical direction, and it's given by this acceleration, or rather, this particular acceleration. So we also have delta upwards is a half 2 omega VE cos lambda times t squared. Omega VE cos lambda t squared. So if you fire in the easterly direction, you will hit above where you aimed in the, by comparison, where you'd be aiming in the northerly direction or the southerly direction. And if you're firing west, then you will find that your bullet is lower than you would have expected. Finally, let's discuss weather systems. Let us consider the Earth, the northern hemisphere, that's a low pressure area, and high pressure outside. So air is attracted to low pressure, but as it does so, it experiences deflection to the right. So we actually have that. This means that in the northern hemisphere, around a low pressure area, you get the air moving in a clockwise direction. Clockwise direction of rotation of storms in northern hemisphere. So this is why hurricanes in the northern hemisphere rotate clockwise. By the same sort of arguments we have in the southern hemisphere, the tropical storms will be rotating anticlockwise. And that concludes our discussion of the Coriolis force and the fictitious forces, or inertial forces, which occur when you consider motion in a rotating frame.